In this video, I'm going to cover galvanic cells and the reduction potential. So we need to know what an electrical current is and what electricity is in order to understand how galvanic cells work. So electrons flow through a conductor in response to an electrical potential difference similar to water flowing downhill in response to a difference in gravitational potential energy. So one way of looking at it is that the electrons are like the water, and when there's a difference in electrical potential from negative to positive in two sides of a conductive material like a piece of metal or something like a metal wire, then those electrons can be pulled from the negative side toward the positive side, similarly to how water is pulled. So electrical current is the amount of electric charge that passes a point in a given period of time. So we can think about those electrons flowing as the carriers of charge, or they could be ions flowing through a solution, which are the carriers of charge. So electric current flowing directly between atoms. In a redox reaction, remember that in the compound that's being reduced is gaining electrons, and the compound that's being oxidized is losing electrons. So electrons are being transferred from one compound to another, from one atom to another. So when the electric current is flowing directly between those atoms, we could hook up two conductive materials. Here's one piece of metal connected by a piece of metal that's hooked up to a piece of metal, that's hooked to another piece of metal and another piece of metal. And remember, metal is a conductive material, so all of these components along the way, maybe copper wire and aluminum clips and a nickel electrode and so on and so forth. So as long as they're conductive material, then the electrons can kind of travel along the metal. So the electrons are going, in this case, from the manganese metal, will lose electrons, and the electrons will travel this way down the wire, and they'll go into the solution, and they'll reduce the nickel 2+ ions in this solution. So electric current flowing directly between the atoms involves the electrons going from one atom to the other, although I wouldn't say necessarily that this is directly between the atoms, because there's a more direct route, which is if I mix this solution and this solution together, the reaction will happen such that the electrons don't have to travel from here all the way over here, all the way over here to get to the next atom. The atom of manganese will be right next to the atoms of nickel. They'll be literally right next to each other, so the electrons can travel a minute distance, a nanometer, right next to each other, instead of having to travel all the way from here to here. So remember, that's the kind of the reason that we separate these two solutions, is that if we make the electrons travel this distance, then I can make the electrons do something. In this case right here, they're not doing anything. They're just going from here to here. But in this case, I can use the electrons that are moving from the anode to the cathode, and as they move this way, I can make them move through a light bulb. And their motion through the light bulb, depending on the electrical potential between the cathode and the anode, might be enough to light up the light bulb. So if we're making the electrons in a redox reaction, if electrons are being transferred between atoms, and we separate the jars and we make the electrons go this way, then we can make them pass through a light bulb, and if the voltage and the current are high enough, then the light bulb will turn on and we can power some device. And remember, the salt bridge is there to balance the charge. So every time an electron goes into this beaker, the charge is becoming more negative. So every time a negative charge comes in from the electron, a positive charge comes in from an ion. And every time a negative charge leaves this compartment, a negative ion enters this compartment through the salt bridge. So we can use the movement of electrons moving in one direction, and we can capture that movement as work and use that energy as work. But of course, as we're using that energy, converting chemical energy to electrical energy to light energy, we're always losing heat. So as the chemical energy is converted to electrical energy, there is heat being lost from that transfer. It's exothermic. and as the electron moves across the wire, there's resistance in the wire, so that heats up the wire, which increases entropy, so there's a loss of some energy there. And of course, as the electrons enter the light bulb and power the light bulb, only about 5 to 10% in an incandescent bulb, only 5 or 10% of that energy is converted to light energy, and the other 90 to 95% is converted to heat. So there, in every different transfer of energy here, we're always satisfying the second law of thermodynamics, and we're always increasing the entropy in the universe. So electrochemistry is the study of redox reactions that produce or require an electric current. So far, we've been thinking about these cells as moving spontaneously, and we can use that spontaneous motion like a ball rolling down a hill or a waterfall or something, and we can use the motion to turn a turbine, for example, or light a light bulb. But we can also run these reactions in reverse to make them require an electric current. And if we run redox reactions in reverse, or it makes a non-spontaneous reaction move from the reactants to the products. So remember, spontaneous just means moving forward without energy, and non-spontaneous doesn't mean it can't happen, it just means we have to put in energy. So we can put in energy in the form of an electric current. The conversion between chemical energy and electrical energy is carried out in an electrochemical cell that we've been looking at. Spontaneous redox reactions take place in a voltaic cell. So when they go forward and we're capturing the energy of that spontaneous forward motion as work, we call those voltaic or galvanic cells. When there's a non-spontaneous reaction that we want to happen, we want to push the ball up the hill, for example, which won't happen by itself. It's not spontaneous, but we can make it happen. It can be non-spontaneous, and we put energy in and push the ball up the hill. So if we put in electrical current to a redox reaction, we can cause a non-spontaneous reaction to happen, and we call those kinds of cells electrolytic cells. And we're adding electrical energy to push the reaction backwards. Oxidation and reduction half reactions are kept separate in half cells. Electron flow through a wire along with ion flow through a solution constitutes the electric current, the electric circuit. It requires a conductive solid electrode to allow the transfer of electrons. So again, it could be metal or it could be graphite. So remember, graphite's made of carbon, but it's actually conductive. So sometimes we see that the electrode in a half cell is made of graphite. It's not made of metal, it's made of carbon. And it also requires ion exchange between the two half cells of the system. So we have to put a salt bridge in. If the salt bridge is not there, the electrons will not move from one cell to the other, because charge will start to build up immediately, and the buildup of negative charge in one cell will push electrons backwards, will push them the other way. So one mnemonic device that we can use to remember the difference between anodes and cathodes is anode equals oxidation, and ox. Cathode equals reduction. It's where reduction occurs. Red cat. So, electrode where oxidation occurs is called the anode. The anode, anions are attracted to the anode. It's connected to the positive end of a battery in an electrolytic cell, and it loses weight in an electrolytic cell. So if oxidation happens at an anode, then that means that oxidation is the process where electrons are lost from a compound. So when electrodes are lost from the anode, they travel from the anode toward the cathode. And the cathode is where reduction occurs. And remember that reduction is when a compound gains electrons. So they're lost from the anode, which is oxidized. The electrons travel to the cathode, where reduction occurs. And so we can remember that an anode is where oxidation occurs, and reduction is where the cathode is where reduction occurs, red cat, and red cat. So anodes are negative and cathodes are positive. Just like anions are negative and cations are positive. So again, the salt bridge is required to complete the circuit and maintain the charge balance. Every time an electron goes in, we gain one negative charge. So every time we gain one negative charge, we also gain one positive charge. So one potassium ion also enters the cell to balance the negative charge. There can't be a buildup of charge here. So if two electrons came in, then overall there would be a -1 charge in this solution. And that -1 charge, when the next electron tried to come in and it saw a negative charge, then the electrons would be repelled, because a negative electron would be repelled by the negative charge in the solution. So that would cause the electron to not enter the cell, and in fact it would repel it and move it backwards. So the cell cannot work unless the charge is balanced. So every time an electron comes in, a potassium ion comes in too. Current is the number of electrons that flow through the system per second. So we usually measure this in amperes, or sometimes we call them amps. So 1 ampere of current, 1 amp of current is 1 coulomb of energy flowing each second. So 1 amp equals 6.242 times 10 to the 18 electrons per second. So when we think about an electrical system, an electrical wire, for example, the current is the number of electrons that are flowing through that electrical wire, through the metal wire, per second. Electrode surface area dictates the number of electrons that can flow. Larger batteries produce larger currents. The voltage is the difference in potential energy between the reactants and products. That's the potential difference. And we call that, we usually measure the voltage, or the potential difference in voltage, or volts. So when we think about this analogy of electricity being like water, and we can make pipes for the water to flow, if I have a pipe that's flat, the water is not going to flow through the flat pipe. One of the first rules of plumbing when you're trying to put drains in your house is that you always have to point the drain downhill a little bit so that the water flows downhill. So we can think about electricity and electrical potentials the same way that we can think about plumbing. If the pipe is flat, the water won't flow. If there's no potential difference, the electricity won't flow. So in order for us to move electrons from one place to another, there has to be a potential difference. So the voltage is kind of like how steep the pipe is pointed. If the pipe is flat, the voltage is 0. If the pipe is pointed downhill at a very steep angle, and the water will go down it very quickly, then we would say that the potential difference is very high. The voltage is very high. So voltage is like how steep is the pipe? How fast is the water going to flow down the pipe when we turn the water on? How fast are the electrons going to move down the potential difference when we complete the circuit? So 1 volt is 1 joule of energy per coulomb of charge. And the amount of force pushing the electrons through the wire is called the electromotive force. So to think about the difference between voltage and amps, back to this analogy, that the pipe. If the pipe is very steep, the water will flow very fast. So if the potential difference is very large, then the electrons will flow very fast, and we'd say we'd have a very large voltage. But if only one electron goes through every second, then I'd say I'd have a very small current. So the electrons, when they do go through the pipe, when they go through this large potential difference, they're moving very quickly, the voltage is very high, but there's not very many electrons, only one per second. So when if I speed up the electrons, or I add more, now I have 1,000 electrons per second. Now the current is high, and the voltage is also high. So that's how we should think about the difference between current and voltage as applied to electrical circuits. The difference in potential energy between the anode and the cathode in a voltaic cell is called the cell potential. The cell potential depends on the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. So the cell potential, how steep that pipe is, what the voltage is going to be in this cell, depends on how easy it is to pull electrons away from the species that's going to be oxidized, and how strongly the species that's going to be reduced is pulling the electrons toward itself. So the voltage of an electrochemical cell is different depending on the thing that's going to be oxidized and the thing that's going to be reduced. The cell potential under standard conditions is called the standard electromotive force, the standard EMF, E naught cell. So this is the electromotive force. It's not the energy, even though they both have a capital E. So remember, the naught stands for standard conditions. Standard conditions are 25 degrees C, 1 atmosphere for gases, 1 molar concentration for all solutions. And the sum of the cell potentials for the half reactions is equal to the standard EMF, or the E naught cell. There are different ways that we can represent cells. We can draw pictures like we've shown before, where there's different compartments and we draw pictures of the electrodes and the solutions. Or we can use a shorthand description of a voltaic cell, where we have electrode, vertical line, electrolyte, 2 vertical lines, electrolyte, vertical line, electrode. And so the oxidation half cell is on the left. So instead of drawing a picture, which would take a long time and maybe you're not a good artist, you can shorthand that by saying, well, the electrode is made of zinc, the metal electrode is zinc, and the electrolyte is zinc nitrate. And that's on the oxidation half cell. And the reduction half cell is on the right. So the electrolyte in the reduction half cell is manganese nitrate, and the electrode is graphite. So the single vertical line indicates a phase barrier. So what that means is that the electrode is solid. It's usually made of metal, but not always. Sometimes it's graphite, but it's usually solid. So if the electrode is solid and the electrolyte is in solution, it's dissolved, then those are in different phases: solid, aqueous. So we put a single line between substances that are in different phases but are in the same half cell. We put a double line to indicate the salt bridge. And so the salt bridge is saying that these two compartments, this compartment over here, where the substances might be in different phases but they're still in the same compartment, that's separated from this compartment over here, where these substances may be in different phases but they're still in the same compartment. So the double line indicates the salt bridge, and it separates the half cells, the oxidation from the reduction half cell. So we can draw the picture and determine which way the electrons are going. They don't always go from left to right, though. We have to look at the oxidation and reduction potentials of the materials, the cathodes and the electrolytes in each of the half cells, in order to determine which way the electrons are going to flow in the cell. So in this case, the anode is on the left, and we know that because the electrons are leaving the anode. The anode is negative, the electrons leave there, that's where oxidation occurs, and the electrons are traveling towards the cathode, which is positive, it's attracting the electrons, and that's where reduction occurs. Those electrons get here and they will reduce something, because reduction is gaining electrons. So we would shorthand this cell by showing that oxidation, the oxidation half reaction is on the left, and what the electrode in the oxidation half reaction is zinc. And we have a phase barrier, and the electrolyte in this cell is zinc 2 plus. So these are in different phases. The solid electrolyte, dissolved zinc 2 plus. So we separate those phases with a solid line. And now we'll talk about the other compartment, and the other compartment is separated by a salt bridge. So the double line represents this salt bridge here. And in this one, the electrolyte is copper nitrate, copper 2 plus, right? And that's separated phase barrier with the solid electrode here, the cathode, which is made of solid copper. So phase barrier, solid copper. Electrodes, the anode is typically made of the metal that is oxidized, and the cathode is made of the same metal that's produced by the reduction, but that's not always true. Sometimes the electrodes do not participate in the reaction. Sometimes the electrodes are what we call inert electrodes. So if the redox reaction we are running involves oxidation or reduction of an ion to a different oxidation state, so maybe the redox reaction we're trying to do is not iron 2 plus to iron 0, iron solid metal. Maybe the reaction we're running is iron 2 plus to iron 3 plus. So there's no solid iron metal involved in the redox reaction. So the electrode does not need to be made of solid iron metal. So sometimes in those cases, we use just an inert electrode. Maybe the electrode is made of platinum. It must be made of something that conducts, so maybe it's made of graphite. Not a metal, but still conductive. But it doesn't have to necessarily be a compound that's participating in the reduction or the oxidation. It could be just some conductive thing, some inert electrode. So, because let's look at another electrochemical cell here. On the oxidation half, again, we see the electrons going from left to right, which seems to be happening a lot in the pictures we're looking at, but it's not always the way that the electrons flow. They don't have to flow from left to right. Their flow is going to be dictated by the species that are in each of these different beakers. For example, if I just flipped these around, then it would look like the electrons were going from right to left. So on the oxidation half here, the anode is made of iron, solid iron, and the electrolyte is iron 2 plus. So we would say solid iron, phase boundary, iron 2 plus. We go across the salt bridge, double line, and in here, look at the reduction reaction. This is pretty complex. We have manganate plus 5 electrons plus 8 H pluses makes Mn2 plus water. So what's actually being reduced? Well, look at the manganese here in this compound, O4. There's 4 oxygen atoms, and each has an oxidation number of -2. So that gives a total oxidation number of -8. And if the total charge is -1, then that would put manganese at +7. +7 plus -8 equals -1. The total charge on the species. So manganese went from +7 to +2. And that takes 5 electrons. That's where these 5 electrons come in. So there is no solid in the reaction. Here I have solid iron going to aqueous iron. But here I have aqueous manganese going to aqueous manganese. There is no solid here. So this electrode does not have to be solid manganese, for example. It can be an inert electrode. It can be made of platinum, some metal that conducts electricity, so it will allow the electrons to enter the solution, but it doesn't have to be part of the reaction. So we still have to put it in our shorthand notation down here, but we don't have to. It doesn't have to be part of the reaction. And the other thing to notice here is that in this reaction, the things that are in solution in my redox reaction are manganate. We don't have to put in electrons. So manganate, H plus, and manganese. So all 3 of those things should be in here, and they're all in the same phase. They're all dissolved. So manganate, aqueous, comma, Mn2 plus aqueous, comma, H plus aqueous. All three of these species are all in this beaker. They're all part of the reduction reaction, so they all need to be included in this representation. But since they're all in the same phase, they're separated by commas instead of by parallel lines. But the platinum is solid, it's not dissolved, so it's separated by a solid line, and it gets its own little space over here. The cell potential, when a half reaction with a strong tendency to occur has a large positive half cell potential, then that means that the electrons are going to flow towards it. So in order for us to determine which way electrons are going to flow in a electrochemical cell, when I hook two different reduction oxidation reactions together, is to look at a measurement that we call the reduction potential. And the reduction potential is just like it sounds. A reaction that has a higher reduction potential means that that reaction has a higher potential to be reduced. That species has a higher potential to be reduced, so it's more likely to be reduced. So when the number is bigger, then reduction is more likely to occur. When the number is smaller, reduction is less likely to occur. Or we could say if reduction is less likely, then oxidation is more likely. So again, when we look at these cells, they often have the electrons moving from left to right, but that's not necessarily the way that they always move. So to determine which way they are going to move, we compare these numbers, the reduction potential. And the species with the highest reduction potential will be reduced. Therefore, the electrons will move toward it. So here we have a reduction potential of plus 0.34 volts, which means copper solid going to copper 2 plus 2 electrodes, or plus 2 electrons. This has a reduction potential of 0.34, and this cathode has a reduction potential of 0. So this is more likely to be reduced, and if it has the electrons and it's more likely to be reduced, then it's not going to give its electrons up. But the reverse reaction would be more likely to occur, because if this had electrons and this has a high reduction potential, a bigger number, a higher potential to be reduced, then the electrons would spontaneously go down to the copper to reduce the copper. So these numbers, the standard reduction potential, we only look at this one way. We don't have reduction potentials and oxidation potentials, although potentially we could. We just usually focus on reduction half reaction, because if we know that something is likely to be reduced, then we already know its oxidation potential. It's not likely to be oxidized because it's either one or the other. And so we know if it has a small potential to be reduced, then it probably has a large potential to be oxidized. So we can't measure the absolute tendency of a half reaction. There is no absolute reduction potential. We can only measure relative reduction potentials relative to some other reaction. And that's because if I try to look at one half reaction by itself, it's not a complete cell. The electrons won't move. The electrons only move when I hook up a complete cell and put the other half on. So, to figure out these numbers in this table of standard reduction potentials, we use a reference electrode that we call the standard hydrogen electrode. And this is a half reaction that's just kind of a standard reference half reaction that we use, which is the reduction of H plus to H2 gas under standard conditions. And this has a potential difference that we just give arbitrarily as 0 volts. And that's just like we say that 0 degrees Celsius is where water freezes. It's an arbitrary number. It's something that we made up. That 0 doesn't mean anything. Water freezing is one thing that freezes, but there's lots of other things that we could have called 0. So in the same way, this H plus being reduced to H2 under standard conditions isn't special. We just chose that reaction to say we're going to set this to 0, and we're going to set everything else relative to this. So we're going to set our temperature scale to 0 degrees Celsius at the freezing of water, and everything else will be relative to that. Of course, we have an absolute temperature scale, which is Kelvin. 0 Kelvin means something, which means that it's the absolute lowest temperature that's possible in the universe. It is the real 0 of the universe. But 0 degrees Celsius doesn't mean as much, because I can definitely get colder than 0 degrees Celsius. That 0 point is arbitrary. So to measure this electrode potential, one way that we could do it is we just hook up the same kind of cell that we have been looking at, a voltaic cell, but instead of putting a light bulb up here, we put a voltmeter that tells us what the voltage is, what the potential is of the electrons moving across this circuit. And on one half reaction of the cell, we hook up the standard hydrogen electrode, where we have H plus, and it's generating H2 gas. And so we can see that as the electrons move this way and they come into the solution, the electrons leave the platinum surface and they reduce the H plus ions, and the H plus ions then form hydrogen gas. So when we measure a potential this way, we call that the standard cell potential, as long as we're at 25 degrees C. So standard hydrogen electrode reduction potential is defined to be exactly 0 volts. The standard reduction potentials compare the tendency for a particular reduction half reaction to occur relative to the reduction of H plus to H2 under standard conditions. Half reactions with a stronger tendency toward reduction than the standard hydrogen electrode have a positive value for the reduction potential. Half reactions with a stronger tendency toward oxidation have a negative value for reduction potential. So again, whether reduction potential is positive or negative doesn't really mean much. It's just relative to the standard hydrogen electrode, which was kind of chosen arbitrarily. So here's the table. At the top, we have the reduction reactions that are most likely to occur, that have the highest, the largest, most positive reduction potential. Those are the most likely to be reduced, and things that are the most likely to be reduced are the strongest oxidizing agents. And down here at the bottom, we have lithium gaining an electron, which has the most negative reduction potential, which means it is the least likely thing to be reduced. So the language is kind of tricky here, but the thing that is a reducing agent means that it is the thing that will cause something else to be reduced. So lithium is a very strong reducing agent because it will not be reduced itself. This number is way too small, but it will help something else to be reduced. Because if it won't be reduced itself, that means it will be oxidized. It means it has a very high oxidation potential. And if it has a very high oxidation potential, that means it's very likely to lose its electron. And if it's very likely to lose its electron, that electron can be used to reduce something. So things that are very likely to be oxidized are reducing agents. And things that are very likely to be reduced are oxidizing agents. So see, as the number gets bigger, those things are more likely to be reduced, and as the number becomes smaller and negative and more negative, those things are less likely to be reduced. Notice that all of the reactions in this table are organized as reductions. Something plus electrons, something plus electrons, something plus electrons. Remember, in a reduction, the electrons always go on the left. In an oxidation, the electrons go on the right, in an oxidation half reaction. So all of the reactions in this table are written as reductions because these are reduction potentials. These numbers here are reduction potentials. So remember, when we're comparing reduction potentials, we're always comparing the tendency of two half reactions to be reduced. And whichever number is bigger says that's the reduction half. But by by process of elimination, it also tells me which parts the oxidation have, because if I compare two numbers, the bigger one is the reduction, and the smaller one is the oxidation. So I only ever need a table of reduction potentials, because once I've determined which thing is the reduction, I also know which half is the oxidation. So I don't need a table of oxidation potentials. So to calculate the cell potentials under standard conditions, we calculate the cell potential. To calculate the cell potential, we have to add the potential of the oxidation half with the potential of the reduction half. So I can look up the reduction potential in a table. I look for the number that's bigger, and that's my reduction potential, and I put that in here. The number that's the oxidation potential, I would have to take the reduction potential and multiply it by -1 in order to turn it into an oxidation potential. In other words, if the reduction potential of this reaction is plus 2.87, then the oxidation potential of this reaction is minus 2.87. And vice versa here. The reduction potential is negative 3.04, but the the oxidation potential is positive 3.04. So to determine the cell potential, I have to add the half reactions together, oxidation and reduction. But I also have to determine, once I know which half is the reduction, I have to do something to the other number in order to turn it into an oxidation potential. I have to reverse it. It has to be multiplied by -1. A redox reaction will be spontaneous when there is a strong tendency for the oxidizing agent to be reduced and the reducing agent to be oxidized. So again, that's like I said, things that are more likely to be reduced are oxidizing agents, and things that are more likely to be oxidized are reducing agents. So higher on the table of standard reduction potentials is a stronger tendency to be reduced, and lower is a stronger tendency to be oxidized. So a redox reaction is spontaneous in the forward direction when the cell potential is negative. So now we know that something is spontaneous in the forward direction when delta G is negative. We just covered that. Delta G is negative, that's spontaneous. Something is spontaneous in the forward direction if the equilibrium constant K is large. And now we have another one. Something is spontaneous in the forward direction if the cell potential is negative. So a half reaction with a smaller or more negative value of the reduction potential is an oxidation, and the half reaction with the larger value is a reduction.